Okay. Ontology for product lifecycle management. And the subtitle is How to Use Ontologies to Build and Fly a Plane, Maintain a Plane, all of those things that belong to traditional product lifecycle management. So Obo Foundry is an ontology suite. There are other ontology suites, the common core ontologies we've already mentioned. There was, until a couple of years ago, a common intelligence community ontology, which was maintained by the Intelligence Community Ontology Working Group. That working group then went defunct for a time, but there are now efforts to bring it back, and then the Common Intelligence Community Ontology will be revivified. It was based on BFO from the very start. There are other ontology suites, and one of them is called the Industrial Ontologies Foundry, which was created by a group of industrial, government, and academic ontology developer communities, with the following goal. If in order to bring about digital manufacturing, you need a terminology for all of the things which are involved in the product life cycle, from design requirements and so forth to productization, testing, and use, and then maintenance and disposal. You need terminologies for all of those things, and every company and every enterprise has its own terminology or terminologies which do not always coincide and which are not logically defined even where they are defined at all. And so the goal is to support interoperability across developers of software to support digital manufacturing by creating a set of high quality ontologies within a framework like the Obo Foundry, but covering industrial engineering and especially manufacturing. Nations who were involved and who are still involved, many of them, and the entire affair is run by NIST. We have regular meetings, several meetings a week, actually, I'm afraid to say, and we have face-to-face meetings roughly once every 4 months. So far, the meetings have been held at NIST or in Buffalo. The next meeting will be held in Oslo, since there are quite vocal European partners in this. And this is something like the way it will look. So we have not yet decided what the top level ontology will be, but as you can imagine, I am working hard to try and convince my colleagues that BFO should be the top level ontology, and that something like the common core ontology should then be the mid-level ontology. And then we will have these other things further down, including a product lifecycle ontology along the lines, roughly, content which I first presented at a meeting in Phoenix, a meeting of an organization called Aircraft Airworthiness and Sustainment, which is a very large industry meeting for designers, manufacturers of engines and aircraft generally. And I gave a talk with this title, which was based on work that I was doing at that time for the Air Force Research Lab on use of ontologies to help create efficiencies in areas like aircraft maintenance. And so the vision, which was presented to myself and to my colleagues at Kubrick, the vision was that every airplane in every use of that airplane, my colleagues at Kubrick, the vision was that every airplane in every use of that airplane is generating huge amounts of data. There are more than 100 sensors in every engine, for instance, which are producing data second by second. And most of this data was not being used. So people didn't know how to use it. And part of the reason is because the data are trapped inside silos. So each relational database is designed to capture data of a certain sort, but it's not designed to be associable with other databases which are designed to capture data of other sorts, and so you can't connect weather data with erosion data and so forth. And so what we wanted was a suite of purpose-built ontologies which would allow tagging of data being collected by aircraft and by maintenance operators and so forth over the life cycle of an aircraft in such a way that we could use. Ontologies are built separately. You have to build the ontologies in tandem with each other so that they can be used to tag all of these disparate data to bring the data together into a framework where they will work together. So we have the data at the bottom, we have the ontologies at the top, and we have software that goes under the heading of OSCAR, which is based on a public domain tool called Karma, which Kubrick then refined in order to enable heavy-duty operations with large amounts of aircraft data, such as I will describe. And the questions that we were aiming to answer are questions like this. So we have a production process. So I can read this and then they can know what that says. So what changes would need to be made in the production process to save time and money while preserving product quality? For that, we need to have data about all stages of the production process. Have the worst rate for bringing about product failures, that kind of question. And then the data look like this. That's testing data. And there's a lot of it, as I say, and there are lots of columns in the data tables. And this is what they look like at a level where you can read. And this is what the ontology looks like. So we have, in blue, we have names of instances. So in the middle there you see act of lot acceptance testing number 3KK6. That's lot acceptance testing is a testing term in the aircraft world. And device number 777, that's an instance of the type product, which is a subtype of the type artifact, which is a subtype of the BFO type object, which is a subtype of the BFO type continuant. So that's how these ontology terms hang together with terms referring to instances. The BFO type object, which is a subtype of the BFO type continuant. So that's how these ontology terms hang together with terms referring to instances. And now what the OSCAR tool does is it creates mappings from the data at the bottom to the ontologies, which appear along the top. And you can't see them here. Maybe you can see them on this. Yes, you can see them here. So these are ontology terms along the top, which are related together through graph theoretically, through object properties, as the OWL people say, relations, as I would say. And because the ontology links because the ontology links term A to term B, and because term A is used to tag column 4 and term B is used to tag column 8, then we can infer from the relation between term A and term B what the relation is between data items in column 4 with a lot of data, primarily testing data. And so you can see more of this as I go down. You can't read any of it. You can read some of that. So that's what we saw before, the lot acceptance testing. And that's a small part of the testing ontology. That's a slightly bigger part of the testing ontology, but now it's joined to the product ontology. And then you can slice and dice these ontology representations. So once the data are tagged with the ontologies, you can slice and dice the data to answer Sparkle queries, as we would say in ontology land. So we can associate all data about, we can find all data about costs which are associated with parts of a certain type from a certain supplier. We can get all that data with all data about costs which are associated with parts of a certain type from a certain supplier. We can get all that data with a very simple query because of the way we've tagged all our data, even though the data is huge and hugely dispersed across many databases. And then we can have Organization 1 produces product 1, that's instance data, using product 2 produced by organization 2. And now tagging the data according to source organization allows us to query not just the parts that are end parts, but also the parts which were used in creating those end parts, so that we can track the flow of failures across the production process. And now very quickly I'm going to go through the product lifecycle ontology that we developed. So we don't need this slide. So this is Bill. Yes?
I'm going to interject here, and I have to apologize because I think when we converted the slides, they're staying online from PowerPoint to the PDF file. I think we lost some of the format.
Yeah, but I think we
get
the intended idea. I don't think there are problems for the viewer. So now the next part is all about building an ontology of the product life. And there are problems for the viewer. So now the next part is all about building an ontology of the product life cycle. And so there are different perspectives on the product life cycle, and some people are only interested in some parts of the product life cycle. So one part of the product life cycle is using the product, and the Air Force uses planes in operations. So they're only interested in this part of the product life cycle. And what does it contain? Well, it contains processes of taxiing, for instance, or sorties, flying, missions. All of those are processes, so they're in yellow. I'm going to use yellow for processes. And then it contains documents. So they have to have a sortie plan. And the sortie plan has to conform to the Air Force planning doctrine. And it has to conform to the Air Force operations doctrine, which in turn have to conform to junctions, processes and documents, or processes as information. And it's just that part which is relevant to C2. And now these are some terms under different headings. So on the left we have terms under the heading process, which include things like flight, inspection, grounding, assessment, and fixing, repairing. Then we have continuance, which means things which continue. For instance, aircraft, but also tails of aircraft, engines of aircraft, but also the functions of the engine. The function of the engine is a continuant. It continues to exist. And then we have information entities, which are clear: tail numbers, part numbers, stock numbers. And now at the bottom in orange we have the product life cycle as seen through the perspective of an acquisitions manager. So the acquisitions manager has or her a material development decision, MDD. This is Air Force talk. I don't know whether this is Navy talk. And this includes a material solution analysis, which is followed by a technical maturity and risk reduction process, then by an engineering and manufacturing development process, and then a production and deployment process, and a maintenance process will come then because it's been deployed. It will fail at some stage, or it will need to be inspected, and then we have the sortie that we saw just a minute ago. So this is what we get if we go back in the history of the product life cycle, which led to that specific sortie. And there are more documents in the picture, and there is engineering in production, development, manufacturing in the picture. And these are the things you have. You have strategy. Well, we need a new plane to do this. Inspection. You have design, you have production, data management, logistics, planning, operation. You have design, you have production, data management, logistics, planning, operations. That's the product life cycle viewed from an aircraft acquisitions perspective. And that's a simpler view of the same stuff without the stuff at the top. And now BFO divides the world into four kinds of entities, really. Things, attributes, information, and processes. And so things we call material entity because they're all made of matter. Attributes we call attributes, information entities, and processes. So that's how the top level organization looks from this perspective. Attributes include qualities, roles, dispositions, capabilities, and functions. But we're not going to worry about attributes. We're going to look just at the other three. So that's the same picture again. We're going to focus on and information entity. We've seen all of that. We know what they are. And processes also, we've seen all of that. Production plan, generation processes, sorties, taxiing, landing, logistics processes. So we have these three headings. We're going to now put them down the left-hand side of the screen, and we're going to track time. So now we're going to do the product lifecycle ontology. Along these three dimensions. So we have BFO has a term process. The product life cycle is a planned process. It's a special kind of process. And it extends through time, like every process, and has various phases. The design process, the production plan generation process, the production process, the maintenance process, the use process, and then the end of life process. We could become more granular. We could have a productization process. We could have multiple use processes or multiple maintenance processes. We could have maintenance, predictive maintenance at the beginning of the life. We could have a productization process. We could have multiple use processes or multiple maintenance processes. We could have maintenance, predictive maintenance at the beginning of the life cycle, and then as we get older, we have more and more needs for more interfering kinds of maintenance. But this is good enough for what we need here, this degree of detail. Each of these is a part of the whole product life cycle process. And each of these is itself a planned process. And so that's the parthood structure of the product life cycle. They're all part relations. And now, here we have the ISA structure of what I just described. Product life cycle is a process, but the design process is a process. So we have both ISA and part of connecting these things together. And now we can add the generic perspective from the manufacturing industry. And now we have the first creation. So the production plan generation process it has as its output a production plan. So product lifecycle doesn't only generate products, it also generates documents, plans, testing reports, and so forth. And they are as important to the product lifecycle process as the product itself. So without the plan, we can't have the product. So the production plan guides the production process, and the output of the production process is a product, and that's the first material entity that we see. That's in gray. So now we have enough information to see where products come from. But now maintenance involves a plan too. So every maintenance process involves some sort of maintenance plan, and that maintenance plan has to be generated. And so we have a generation process, which is part of the product life cycle. And that, when we put it all together, looks like this. So we have a production plan generation process, which generates a production plan, which guides the production process, and we have a maintenance plan generation process which has as its output a maintenance plan which guides a maintenance process. And then the maintenance process has as its output a maintenance report. And this part we already have seen, and this part we now put together. We've seen all of this. We put now requirement specification, which came from an earlier part of the product life cycle. The drawing, the product model, is an output of a design process, which is an input to the production plan generation process, and so on. And now we get more documents, so we still have the sortie. We get more documents, so we still have the sortie. The operation is the use of the aircraft, the mission, the flight, the Air Force doctrine guiding all of the planning for the sortie. And now we have logistics plan, logistics doctrine, maintenance history, maintenance report. Somewhere in here we'll have testing. We have a technical manual which guides the formulation of the maintenance plan. We have the flight manual which guides the operation of the aircraft. And now we have many more gray things, because we now have to take into account all the material entities, which the people, the facilities, the factories, the landing sites, the aircraft themselves, the waste material which result from disposing of the aircraft. All of these things are part of the product life cycle. The utility supply for energy, water of the aircraft. All of these things are part of the product life cycle. The utility supply for energy, water, data, and so forth. And then this is a simple view of where the aircraft starts. It starts with raw material and it ends as waste material. And there is an end-of-life process. And that end-of-life process needs an end-of-life plan, which guides the end-of-life process. And I figure that would be a good slide to end with.
Okay, fantastic. So it's the end of part 2. We have one question so far. So if you have any other questions, please send them in via the chat. So the first question is, are any of the existing ontologies shown in the first part of the part 2 of the brief able to be linked to an Navy? Send them in via the chat. So the first question is, are any of the existing ontologies shown in the first part of the part 2 of the brief able to be linked to an Navy acquisition ontology?
So I did this work for the Air Force a year or so ago, and in the back of my mind through all of that work was the idea that it would be really good to have an acquisitions ontology, not just for the Air Force but for the DoD generally. Now, the Navy SYSCOMs, with whom I have been working only for a few weeks, are in the business of acquisition, and I think that. So I'm sitting next to the person who is in charge of the project, and I haven't yet dared to express to him the idea that this would be a good starting point for building a Navy acquisitions ontology. So now, so we will be building something like that for the Navy, and I made the point this morning that presumably there is very little difference between aircraft systems in the Navy and aircraft systems in the Air Force, and I was immediately disabused because I'm clearly ignorant of how different the two sets of systems are. But I'm still convinced that there would be a lot of commonality between those two. So in building the aircraft systems ontology for the Navy, I will do my very best to ensure that there are a level which you can go down which is common to the two, and then they split somewhere in the middle.
Fantastic. It looks like we've got a couple more people typing, so we're going to hold for just a second and see if any of these questions come in.
I have a quick question, actually.
We have a question in the room.
You skipped over it quite quickly, but you listed the 4 main things that are within the ontology.
Do we need to repeat that? Yes. So the question is as follows. I started off with the 4 upper level terms: material, entity, attribute, process, and information entity. But BFO has a number of lower level terms. The question was, how do I get from BFO to those lower level terms, and then how do I get from those lower level terms to the terms I was using in the actual product lifecycle ontology, for instance, end of life plan or end of life process? So the answer to the first part of the question is BFO has more than just those 4 terms. They are really just the very top, and then things divide as you go down. So things are divided actually into things and their parts, and then aggregates of things. So an organization is not a thing, it's an aggregate of things. And those terms are already in BFO and they're defined in BFO, and so by using BFO you get them for free. But then once we get to the domain level, then we need to work out how we define something like an end-of-life process. And an end-of-life process in the context of a product lifecycle ontology would be a part of the product lifecycle which has as input a product and has as output either waste material or material for recycling, or I don't know what the other options might be, a museum piece. Or so that would be the definition. And you do the same, you just have to do the work. And having the surrounding ontology makes that work much easier, of course. So I built the ontology by creating these PowerPoints, and then the defining, writing all the axioms was just a matter of reading from the PowerPoints, but then finding errors and checking them, and then adding more information. And
okay, another question. Do any of the major DoD contractors use Ontology for acquisition, design, or PLM? And PLM is
product lifecycle management. Yes. So my guess would be no, but they're trying. So the acquisitions connection artifact that I referred to earlier is an attempt. It's an attempt. At least they're moving in the right direction. They just don't know what the principles are that you should use in order to build an ontology. Now, whether there are other such attempts, I simply do not know. I think the Industrial Ontologies Foundry has Air Force people who attend the meetings. The meetings. We also have Navy people who are attending those meetings. But the relationship between the Navy SYSCOMs ontology work and the Industrial Ontologies Foundry is still to be determined.
Are any of the major DoD contractors involved in the Industrial Foundry?
No. No, it's people like Mark Blackburn.
Okay.
Yeah. But you could join.
Okay, regarding an aircraft systems ontology, how will this new set of definition be resolved with or affect non-ontological definitions such as the aircraft product breakdown structure defined by Mill Handbook 881?
Good. So I would say it would go in the opposite direction. When we are building an ontological breakdown of the parts of an aircraft, we would start from things like that mill standard that you're referring to here. So we would are building an ontological breakdown of the parts of an aircraft, we would start from things like that mill standard that you're referring to here. So we would not try and reinvent the wheel. We would use authoritative standards wherever possible. So and we would be bending over backwards to be consistent with standards in this kind of field, because the breakdown, I'm assuming, is incredibly complicated. And we already did do some of that work. The Common Core Ontologies does indeed contain, I believe,